Right now, the nearest star beyond our own sun sits at a distance of 4.2 light-years. That number sounds manageable. Astronomers refer to it as our cosmic neighbor. Science fiction authors treat it as the obvious first destination for a species reaching outward into the galaxy. Mission architects include it in their proposals as though proximity alone makes it plausible. But the moment you try to actually go there, something shifts. Something fundamental and cold settles into the calculation. The fastest spacecraft humanity has ever launched would require more than 70,000 years to complete the crossing. Any message transmitted home would not reach Earth for over 4 years. No vessel dispatched in response to a distress call could ever close the gap in time to matter. No supply mission could ever find you. The distance is so absolute that the word nearest, a word that exists to communicate accessibility, to suggest that something is within reach, becomes a quiet deception your intuition constructs to protect you from the full weight of the truth. The closest star in the entire universe is already so remote that the act of traveling to it may be fundamentally incompatible with human existence as we know it. If you want to understand why the nearest star is already the most terrifying destination our species could ever attempt, do me a small favor and hit that like button and subscribe. It genuinely helps this channel reach people who need to hear this. Now get yourself comfortable, settle in, and take a slow breath. Let's begin. On a clear night, from anywhere in the southern hemisphere, look up and find the constellation Centaurus. Trace its ancient geometry against the dark. Somewhere inside that familiar pattern of lights, there is a star so faint that no human being in recorded history has ever spotted it without the aid of a telescope. It produces barely 1/20th of 1% of the luminosity our sun generates. Its mass is roughly 12% of the sun's. Its diameter measures approximately 15% of the sun's width. If you were to remove our sun from the center of the solar system and place this object in its position, the Earth would freeze within days. Midday would resemble a permanent, deep dusk. The oceans would begin to solidify before the first week had passed. The photosynthetic processes that sustain nearly all life on the surface would fail within months as the light levels dropped below the threshold plants require. Every ecosystem built over billions of years would begin collapsing in the dark. This dim, barely glowing cinder of a star is called Proxima Centauri, and it carries a title that reads like an open door but functions like a locked gate. It is the nearest star to our solar system, the closest sun beyond our own, the first conceivable stop for any civilization that has begun dreaming of other worlds. That designation echoes through decades of textbooks, science fiction, mission white papers, and public imagination. Nearest. The word is soft. It carries the warmth of proximity. It implies that something is close enough to be relevant, close enough to be attempted, close enough that the conversation about reaching it is not entirely abstract. It whispers to us in the language of possibility. But that whisper is not truthful. It is not a deliberate misleading. It is not a conspiracy dressed in the language of astronomy. It is something more insidious than either of those things. It is a lie that our own language tells us, with complete sincerity, because the human brain was built to navigate a small, rocky world and was never equipped with the neural architecture required to truly comprehend what 4.24 light-years means the moment you attempt to cross it. The word nearest is doing its honest best to translate an interstellar distance into human terms. It simply does not have enough to work with. Proxima Centauri was first identified in 1915 by Robert Innes, a Scottish-born astronomer stationed at the Union Observatory in Johannesburg, South Africa. Innes was engaged in the painstaking work of comparing photographic plates of the southern sky, images taken at different times, laid side by side, examined for differences when he noticed a star exhibiting an unusually rapid proper motion. It was moving across the background of the sky at a rate faster than nearly any other object observed at that distance. That speed was the diagnostic clue. Stars that appear to shift quickly against the fixed backdrop of the more distant universe are typically close, for the same reason that a hawk skimming the treetops outside your window seems to move faster than a jet airliner at cruising altitude across a distant sky, even though the airliner covers far more ground in absolute terms. The nearby object sweeps through your field of view quickly because it is nearby. Innes measured the parallax of this dim star, the tiny but detectable shift in its apparent position as Earth orbited the Sun from one side to the other, and the measurement confirmed what the proper motion had suggested. This faint object sat closer to our solar system than any other known stellar body. He named it Proxima, from the Latin word for nearest. The name adhered cleanly to the object, and for more than a century since, it has been gently, quietly misleading every person who hears it for the first time, and allows the meaning to register as comfort. Proxima Centauri does not travel through space alone. It is a member of a triple stellar system. The two dominant stars of that system, designated Alpha Centauri A and Alpha Centauri B, orbit each other in a gravitational embrace that takes approximately 80 years to complete one full cycle. Their separation during that orbit varies, but averages out to a range roughly comparable to the distance between our Sun and Uranus. These two stars are, in cosmological terms, not dramatically different from our own Sun. Alpha Centauri A is marginally more massive, a degree hotter, and slightly more luminous. Alpha Centauri B runs a little cooler, a little smaller, and a little dimmer. Together they form a binary pair that is visible without optical aid from the southern hemisphere, appearing as the third brightest stellar system in the night sky, a single brilliant point that only a telescope resolves into two. Proxima circles this central pair at an extraordinary remove. The separation between Proxima and its two brighter companions is approximately 13,000 astronomical units, 13,000 times the distance from Earth to the Sunday. At that distance, Proxima takes roughly 550,000 years to complete a single orbit around Alpha Centauri A and B. The figure is almost impossible to process. 550,000 years. In that span of time, the last ice age came and went. Anatomically, modern humans arrived, spread across every continent, built every civilization that has ever risen and fallen, developed writing, mathematics, agriculture, industry, and spaceflight, and by that point had not yet watched Proxima complete a single circuit of its distant companions. For generations of astronomers, the gravitational connection between Proxima and the Alpha Centauri binary was a matter of genuine scientific debate. Perhaps Proxima was merely passing through the same neighborhood by coincidence, an unbound wanderer following a similar trajectory by chance. Modern velocity measurements settled the question. Proxima is gravitationally tethered to the system. It belongs to the family, but it orbits its relatives at such a staggering distance that the family bond is the weakest imaginable, a whisper of gravity stretched across thousands of astronomical units. In the formal language of stellar classification, Proxima Centauri is an M-type main sequence star, specifically categorized as M5, 5V. Red dwarfs of this category represent the most common variety of star in the Milky Way. They account for approximately 70% of all stellar objects in our galaxy. The universe, it turns out, vastly prefers small, dim, extraordinarily long-lived stars over the more dramatic varieties we tend to picture when we imagine suns. Red dwarfs burn hydrogen with a frugality that defies easy comparison. Where our sun will exhaust its core hydrogen supply in roughly 5 billion years, triggering the expansion into a red giant that will eventually engulf the inner planets, Proxima Centauri will still be fusing hydrogen perhaps 4 trillion years from now. 4 trillion. The current age of the universe is approximately 13.8 billion years. Proxima will outlive that figure by a factor of nearly 300. Long after our sun has swollen, scorched the inner solar system, shed its outer layers, and cooled into a white dwarf, slowly radiating its remaining heat into the surrounding void, Proxima Centauri will be burning. Long after most of the stars visible in tonight's sky have completed their full life cycles and gone dark, Proxima will be there. Dim, patient, enduring. The last fires to go out in this corner of the galaxy. This extraordinary longevity is part of what makes Proxima Centauri scientifically compelling, but it is also part of what makes the star subtly deceptive. A star that will outlive nearly everything else in the observable universe feels permanent, and permanence carries a quiet implication of accessibility. The star will wait. It will not evolve into something hostile. It will not die before we arrive. it will still be there, still burning, however dimly. And things that will wait for us have a way of feeling reachable, even when they are not. But Proxima is not waiting in any sense that matters to the crossing. It is simply sitting at a distance that must be pulled out of the polite abstraction of the term light year and converted into numbers that carry actual weight. 1 light year is the distance that light travels through a vacuum during the span of 1 complete Earth year. Light moves at approximately 186,000 miles per second. In the time it takes to blink, light has traveled roughly 1,000 miles. In 1.3 seconds, it crosses the gap between the Earth and the Moon. In 8 minutes, it crosses from the Sun to the Earth. In roughly 4 hours, it reaches Neptune. In less than a day, it exits the loosely defined outer boundary of the solar system, and then it travels for 4 more years before it reaches Proxima Centauri. 4.24 light years. Converted into familiar units, that figure becomes approximately 24.9 trillion miles, 40.2 trillion kilometers, 24.9 trillion miles. Hold that number for a moment and observe what happens inside your own mind as you try to process it. Your brain does something automatic and unavoidable. It rounds, it abstracts, it classifies the number as very large and moves on to the next piece of information because the human cognitive system did not evolve to distinguish viscerally between 1 trillion and 24 trillion. Both register as incomprehensibly large. Both produce the same vague, unsatisfying sense of enormity without any corresponding physical intuition to anchor the feeling. That cognitive flattening, that inability to feel the difference between 1 trillion and 25 trillion, is precisely where the deception takes root. Because 24.9 trillion miles is not just a large number. It is a number that breaks every analogy you have ever used to make distance feel manageable. Consider this. If you sat down behind the wheel of an ordinary car and drove at a steady 65 miles per hour, without ever stopping, without sleeping, without pausing for fuel, along a straight highway extending from the Earth to Proxima Centauri, your journey would last approximately 44 million years. 44 million years at highway speed. When your hypothetical car first pulled onto that road, the Indian subcontinent had not yet completed its collision with Asia. The mountain range we call the Himalayas was still in the process of being thrust upward by that tectonic impact. The Mediterranean Sea was near the end of an extraordinary geological episode during which it had essentially dried out entirely, a vast evaporation event that geologists call the Messinian salinity crisis. Apes had not yet diverged from the lineage that would eventually produce monkeys. The entire sweep of primate evolution that culminates in a human being sitting in a car reading these words would unfold in its entirety, begin to finish, before the car reached its destination. The engine would need to run for a span of time more than 2,000 times longer than the total existence of the human species, or approach the scale from a different direction. Standard United States paper currency, each bill measuring 6.14 inches in length, would need to be laid end-to-end in a chain approximately 257 quadrillion bills long to span the distance from Earth to Proxima Centauri. The total sum of all money in circulation across the entire world, every currency, every denomination, converted to dollars, is estimated at roughly 40 trillion. You would need to multiply every dollar currently in existence by more than 6,000 and still fall short of building a physical chain of paper currency that reaches the nearest star. The bills themselves, stacked or laid flat, would represent a mass exceeding that of a substantial asteroid. And for the overwhelming majority of that chain, no planet, no moon, no rock, no detectable concentration of matter would exist close enough to be seen, just the paper stretching into nothing. This is the true translation of 4.24 light years when you refuse to let it remain an abstraction. It is not large in the way that a mountain range is large, or in the way that an ocean is large. Human civilizations have crossed mountains and oceans. They have mapped them, named them, built routes across them. Those are scales that our history has digested. The distance to Proxima Centauri is large in a fundamentally different register. It is large in a way that mocks the very concept of crossing. It is a number that sits inside the vocabulary of astronomy, wearing the costume of a neighborly descriptor, while representing a gap so extreme that every road, every vehicle, every bridge, every vessel ever constructed by human beings becomes irrelevant noise on the scale required. And here is where the psychology of the word nearest does its most lasting damage. When a person hears that Proxima Centauri is the nearest star, the brain performs a comparative operation automatically and without conscious effort. Nearest means closer than the alternatives. It means the minimum version of the difficulty. It means the best case that interstellar space offers. That framing produces a ghost of hope, the dim but persistent feeling that because this is the closest, it must be somehow within reach, or at least closer to within reach than anything else on offer. The word nearest creates a psychological foothold that the actual distance immediately shatters, but by then, the foothold has already taken root. Nearest, applied to Proxima Centauri, functions the way shallowest functions when applied to the deepest parts of the ocean. The Mariana Trench descends to nearly 36,000 feet below the surface. If you were told that the shallowest point of the deep abyssal floor was only 12,000 feet down, you might briefly feel a flicker of relief. 12,000 sounds better than 36,000, but you would still be annihilated by pressure long before you arrived, without a vehicle specifically engineered to survive conditions that exist nowhere else on Earth. The shallowest abyss is still an abyss, and the nearest star is still a stellar body separated from us by a vacuum so wide, so empty, and so indifferent to the urgency of any crossing that the journey to reach it reduces every human mode of travel to a rounding error. The nearest star, the easiest case, the minimum difficulty, and already it is already impossibly far. The cruelty deepens the moment you learn what actually exists at the destination, because Proxima Centauri is not merely a star burning alone in the dark, it is a star with worlds. And at least one of those worlds orbits within the zone where liquid water could exist on a surface. The nearest star is not an empty endpoint, it is a system. And that fact transforms the distance from an abstract scientific measurement into something far more personal, far more tormenting, a gap between here and a place that might actually matter. In 2016, a team of astronomers working with the European Southern Observatory's HARP spectrograph published a result that sent a visible shock through both the scientific community and the wider public imagination. They had detected a planet orbiting Proxima Centauri. The instrument works by detecting the radial velocity signature of a planet, the tiny but measurable gravitational tug that an orbiting body exerts on its host star, causing the star to wobble slightly toward and away from us as the planet circles it. That wobble stretches and compresses the wavelengths of the star's light in a pattern that, with sufficient precision, reveals the presence, mass, and orbital period of an unseen companion. What HARPS detected was a planet completing one full orbit every 11.2 Earth days, circling Proxima Centauri at a distance of approximately 4.5 million miles. That orbital distance is more than 20 times closer than the Earth sits from our Sun. At first glance, this sounds like the recipe for a roasted, airless rock. But Proxima Centauri is not our Sun. It is a dim red dwarf radiating a tiny fraction of the energy our star produces. And because it radiates so little, the zone where temperatures could theoretically permit liquid water on a planetary surface, the region astronomers call the habitable zone, sits far closer to the star than the equivalent region around our Sun. The 11-day orbit places this world, designated Proxima Centauri b, squarely within that zone. Its estimated minimum mass sits at approximately 1.05 Earth masses, a rocky world, similar in size and likely in bulk composition to our own planet, orbiting in the habitable zone of the nearest star. The words landed like something historic. An Earth-sized planet, habitable zone, nearest star. The phrasing felt like a statement the universe had been withholding for years and had finally, quietly released. Here was a world, not a gas giant, not a barren ice moon at the edge of some distant system, but an Earth-sized rocky body potentially capable of holding liquid water on its surface, circling the star closest to our own. The planet was real, the orbit was confirmed, the mass was measured, and it was right there, at the nearest possible address in the entire galaxy. But Proxima Centauri b does not exist in isolation, and it does not exist without complications. The star it orbits is not a stable, gentle emitter like our Sun. Proxima Centauri is classified as a flare star, an eruptive variable, in the formal language of stellar physics, meaning it is prone to sudden, violent outbursts of electromagnetic energy that dwarf anything our Sun produces on a routine basis. In 2019, astronomers monitoring Proxima using multiple instruments simultaneously detected the largest stellar flare ever recorded from the star. For a brief period, Proxima Centauri blazed approximately 14,000 times brighter than normal in ultraviolet wavelengths. 14,000 times. The burst was so intense that if Proxima b possesses an atmosphere anything like Earth's, that single event would have delivered an ultraviolet dose to the planet's surface, comparable to thousands of times the radiation that would be lethal to most life forms we know. These eruptions are not rare anomalies. They are a defining feature of the star's behavior. Red dwarfs of Proxima's type are among the most magnetically active stars in the galaxy. The same slow-burning nuclear efficiency that gives them their extraordinary longevity also produces a deeply convective interior that generates intense, tangled magnetic fields. Those fields build tension over time and release it in explosive reconnection events, flares that hurl radiation and charged particles outward at velocities that can strip the outer layers of a close-orbiting atmosphere the way a sandblaster strips paint from metal. Whether Proxima b retains a meaningful atmosphere at all remains one of the most consequential open questions in contemporary planetary science. A planet that began its history with a rich atmosphere could have had that envelope steadily eroded by billions of years of Proxima's flaring activity. If the planet lacks a magnetic field strong enough to deflect the incoming charged particles, and its proximity to the star, combined with the likely tidal locking of its rotation, makes the generation of a robust planetary magnetic field uncertain, then the atmospheric stripping may be essentially complete. The world may be a bare, irradiated rock with nothing between its surface and the star's violence, or it may not. Some theoretical models suggest that certain atmospheric compositions, particularly those rich in carbon dioxide or molecular hydrogen, could survive even aggressive stellar bombardment under the right conditions. Volcanic outgassing could replenish lost gases over geological timescales. A thick enough initial atmosphere might retain a survivable remnant even after billions of years of flare exposure. The answer is genuinely unknown, and it will remain unknown until instruments powerful enough to characterize the atmosphere directly are brought to bear on the planet. There is also the question of tidal locking. Because Proxima b orbits so close to its star, the gravitational interaction between the two bodies almost certainly forces the planet to rotate with the same face perpetually aimed at Proxima Centauri, the way the Moon always shows the same face toward Earth. This means one hemisphere bakes in constant dim starlight, while the other hemisphere endures permanent night and temperatures far below freezing. The terminator line between these two extremes, a perpetual ring of twilight circling the planet, might be the only region where temperatures remain in a range hospitable to liquid water, if the atmosphere is thick enough to redistribute heat around the globe. But whether such redistribution occurs, and whether the result is a stable habitable band or a system of violent atmospheric convection cells and hypercanes, is a matter of active modeling with no observational confirmation yet available. This is the particular torment of Proxima b. It might be habitable. It might be a scorched, airless, radiation-scoured ruin. The uncertainty itself is not neutral. It is a specific kind of anguish, the anguish of not knowing whether the nearest Earth-sized world in the habitable zone of the nearest star is a place worth everything it would cost to reach. The goal might be real. It might be nothing. And the only way to find out is to either develop instruments powerful enough to read the chemistry of an atmosphere 4.24 light-years away, or go there. One of those options is approaching feasibility within decades. The other is the subject of this entire journey. Proxima Centauri does not host only one confirmed world. In 2020, astronomers proposed a second candidate planet based on additional signals in the radial velocity data designated Proxima Centauri d. This object would be extraordinarily small by planetary standards, its minimum mass estimated at roughly 1/4 of Earth's mass, making it lighter than Mars and among the least massive exoplanets ever proposed through radial velocity detection. It orbits Proxima every 5.15 days at a distance of approximately 4 million kilometers, placing it closer to the star than Proxima b and well outside the habitable zone. In 2025, the NIRP's instrument, the Near-Infrared Planet Searcher, operating on the European Southern Observatory's Very Large Telescope, independently confirmed Proxima d's existence through high-precision radial velocity measurements, achieving accuracy on the order of tens of centimeters per second. That level of precision detecting the gravitational signature of an object lighter than Mars pulling on a star 4.24 light-years away represents one of the most technically demanding measurements in the history of observational astronomy. Proxima d's confirmation added a second verified member to the planetary retinue of the nearest star. It is almost certainly not habitable. A world with 1/4 of Earth's mass orbiting so close to an active flare star would struggle to retain any meaningful atmosphere. It is likely a bare, battered rock, perhaps geologically active, perhaps simply inert, circling its dim sun every 5 days in perpetual ultraviolet bombardment. But it is real. It is there. Another world at the nearest star, confirmed by instruments on a mountain in Chile, measuring the barely perceptible wobble of a star more than 40 trillion kilometers away. A third planet, Proxima Centauri c, was proposed in 2019 based on a longer period signal in the radial velocity data. The candidate was described as a more massive body, perhaps 6 Earth masses orbiting far beyond the habitable zone with a period of approximately 5.2 years. If real, it would likely be a cold super-Earth or mini-Neptune-class world, too distant from its already dim star to permit liquid water and too far out to be significantly affected by the flaring activity that bombards the inner system. For several years, Proxima c occupied an ambiguous status in the literature. Some analyses supported it, others raised doubts. Tentative evidence from Hubble Space Telescope astrometry appeared to corroborate the signal. A possible direct imaging detection was reported using the Sphere instrument at the Very Large Telescope, though the researchers themselves acknowledged the detection was marginal and uncertain. Then in 2025, the same NIRP's observations that confirmed Proxima d delivered a decisive blow to Proxima c's candidacy. The high-precision dataset was unable to recover the radial velocity signal that had originally been attributed to the outer planet. A weak periodic signal appeared at a similar orbital period, but at a significantly lower amplitude than the original claim, insufficient to constitute a confirmation. The candidate was downgraded from probable to inconclusive, and as of early 2026, Proxima c's existence remains undemonstrated. The nearest star's planetary inventory, as currently confirmed, consists of 2 worlds, the potentially habitable Proxima b and the tiny, scorched Proxima d. One world that might matter enormously, and one that almost certainly does not. This planetary census changes the texture of the journey's impossibility in a specific and pointed way. The destination is not empty. The nearest star is not a barren endpoint sitting in the void with nothing to recommend it. It is a system with structure, with worlds, with at least one object that occupies the precise orbital range where life as we understand it could theoretically exist. The system is real. The planets are confirmed. The instruments needed to characterize Proxima b's atmosphere in detail are under construction right now in the mountains of northern Chile, where the extremely large telescope, a mirror 39 meters across, the largest optical telescope ever built, is scheduled to begin observations in the latter half of this decade. When that instrument turns its aperture toward Proxima Centauri b, it may be capable of detecting oxygen, methane, water vapor, or carbon dioxide in the planet's atmosphere. It may find the chemical signatures that, on Earth, are the exhaled products of biology. It may find the spectroscopic evidence of a living world, and it will find all of that from here, through instruments, through photons, through data encoded in the wavelengths of light. that passed through or reflected off a planetary atmosphere 4.24 light-years away and traveled that entire distance to fall on a mirror in the Atacama Desert. We will know it the way you know what is inside a photograph, not the way you know what is inside a room you have entered. There is a specific variety of suffering that belongs to knowing exactly what you cannot reach. A person who has never seen the open sky does not ache for it in the same way as a person who can see it through a window sealed with glass they cannot break. Proxima Centauri b is the sky through the glass. The glass is 24.9 trillion miles of vacuum, and the instruments we are building will make the view through that glass progressively clearer, progressively more detailed, progressively more certain, while the glass itself remains as impenetrable as it has ever been. We may one day confirm with high confidence that life exists at the nearest star. We will confirm it from a distance that makes the confirmation feel like a cruelty dressed as a discovery. The astronomers doing this work are not being cruel. They are doing extraordinary science, science of a precision and ambition that was not imaginable a generation ago. The NIRPS instrument that confirmed Proxima d achieved radial velocity sensitivity that would have seemed impossible as recently as the early 2000s. The extremely large telescope, when it achieves first light, will carry humanity's observational reach into territory that current instruments cannot access. The science advances. The knowledge accumulates. The picture of the nearest star and its planetary companions sharpens year by year, and the distance stays exactly the same, 24.9 trillion miles, 4.24 light-years, the same number it was when Robert Innes first noticed that dim, fast-moving point of light on a photographic plate in Johannesburg in 1915. The same number it will be when the extremely large telescope captures its first spectrum of Proxima b's atmosphere. The same number it will be when those spectra reveal oxygen and methane in ratios that cannot be explained without biology. The measurement changes. The instruments improve, the knowledge grows, the gap does not move. What comes next will alter how you think about that gap in ways that go far beyond the abstract, because so far, all we have discussed is the distance itself, the scale of the void, the size of the number, the nature of the destination. Distance is geometry. Distance is measurement. Distance can, in principle, be divided by speed, and so the next question, the only question that matters for anyone who has ever looked at Proxima Centauri and allowed themselves to wonder how long would it actually take to get there, demands an answer. And the answer is where this story stops, being merely sobering, and begins being something closer to devastating. Speed is the only variable that offers any hope. The distance is fixed. The destination is set. The void between here and Proxima Centauri is not negotiable, not compressible, not subject to revision by any technology currently within our reach. But speed is something humanity has been increasing, methodically and sometimes dramatically, for as long as we have been building things designed to move. And so when the mind confronts the scale of interstellar distance for the first time and searches for the exit, speed is where it reaches. If the distance cannot change, perhaps the time can. Perhaps the journey can be made short enough, fast enough, that the word crossing begins to feel honest. The search for that comfort begins with the fastest objects humanity has ever sent beyond the Earth, and it ends badly. Voyager 1 was launched on the 5th of September, 1977. At the time of writing, it has been traveling continuously for more than 47 years. It carries no fuel for acceleration, it is purely coasting now, moving by inertia alone, propelled by the gravitational assists it received from Jupiter and Saturn during its early trajectory through the outer solar system. Those planetary flybys accelerated it to a velocity that no rocket burn alone could have produced economically. Today, Voyager 1 travels at approximately 38,000 miles per hour relative to the Sun, or roughly 10.7 miles per second. It is the most distant human-made object in existence. As of 2026, it sits at approximately 23 billion miles from Earth, somewhere in the interstellar medium beyond the heliopause, the boundary where the Sun's outward-flowing solar wind finally loses the battle against the pressure of interstellar gas and turns back. Voyager 1 has crossed that boundary. It is, in the strictest sense, in interstellar space. It is already there, beyond the solar system, in the void between stars. At its current velocity, Voyager 1 would require approximately 73,000 years to reach Proxima Centauri. 73,000 years. Anatomically modern humans first appeared between 200 and 300,000 years ago. The crossing to the nearest star, at the speed of humanity's fastest currently operational spacecraft, would consume roughly a third of the entire span of human existence on this planet. It would consume the equivalent of the entire recorded history of every civilization humanity has ever built, repeated approximately 36 times consecutively. It would outlast every language currently spoken on Earth by a margin of perhaps 60,000 years. Whatever society launched such a vessel would bear no recognizable relationship to whatever society's distant descendants might intercept its signal upon arrival. The word descendants itself barely applies the genetic, cultural, linguistic, and institutional continuity required to maintain any meaningful connection across 73,000 years of human history does not exist, has never existed, could not exist. Voyager 1 is not going to Proxima Centauri in any meaningful sense. It is heading, by coincidence of trajectory, in the approximate direction of a different star entirely, AC plus 793888, a red dwarf in the constellation Camelopardalis, and it will pass within approximately 1.6 light-years of that object, in approximately 40,000 years. Not Proxima, not even close to Proxima, and at 1.6 light-years, it will still be nowhere near anything. The Parker Solar Probe represents the other end of the speed spectrum available to current human technology. Launched in August 2018, the probe was designed to approach closer to the Sun than any previous spacecraft, swooping within a few million miles of the solar surface in a series of gradually tightening elliptical orbits. During its closest approaches, the Parker Solar Probe has achieved velocities that dwarf anything in the Voyager family. In December 2024, during its closest perihelion pass to date, the probe reached a peak velocity of approximately 430,000 miles per hour, roughly 632 feet per second. It became briefly the fastest human-made object in recorded history. Headlines announced it with justifiable enthusiasm. The number is genuinely astonishing by any ordinary standard of reckoning. At 430,000 miles per hour, the crossing to Proxima Centauri would require approximately 6,400 years. The Parker Solar Probe, the fastest machine humanity has ever built, traveling continuously at its maximum velocity, not the velocity it maintains during most of its orbit, but its peak perihelion speed, which it achieves only momentarily before the Sun's gravity begins pulling it back, would need 6,400 years to reach the nearest star. 6,400 years ago, the Egyptian Old Kingdom had not yet been established. The pyramids of Giza would not be built for another 500 years. Writing had only recently been invented, and in only a handful of places. Every civilization, every empire, every technological tradition that has arisen and collapsed in the entire span of human history fits inside the journey time of the fastest machine we have ever made. These two data points, 73,000 years for Voyager's coasting velocity, 6,400 years for Parker's peak velocity, define the current envelope of human achievement in propulsion. Neither number is remotely useful for interstellar travel in any time frame that involves human beings or their descendants in any recognizable form. They demonstrate, with brutal clarity, that chemical and gravity-assist propulsion, the technologies that have carried everything we have ever launched beyond Earth orbit, operate in a regime roughly 4 to 5 orders of magnitude too slow for the task at hand. The engineering community has not ignored this constraint. For decades, researchers in the field of advanced propulsion have explored alternatives to chemical rockets, alternatives that could theoretically close some portion of the speed gap between what we currently achieve and what an interstellar crossing demands. These proposals occupy a wide spectrum from the technically plausible to the physically permitted in principle but practically remote. Nuclear thermal propulsion replaces the chemical combustion of rocket engines with the heat produced by a nuclear reactor, a working fluid Typically, hydrogen is passed through or around a reactor core, heated to extreme temperatures, and expelled through a nozzle. Because nuclear reactions release far more energy per unit of mass than chemical combustion, a nuclear thermal rocket can achieve a higher exhaust velocity than any chemical system, which translates directly into greater efficiency. The concept is old. NASA's NERVA program, which ran from the 1960s into the early 1970s, demonstrated nuclear thermal rocket engines in ground tests, achieving performance that genuinely exceeded the best chemical systems. The program was cancelled in 1972 for budgetary and political reasons, not technical ones. Modern nuclear thermal propulsion concepts, building on that legacy, propose specific impulse values, a measure of fuel efficiency roughly twice those achievable with the best chemical engines. Applied to an interstellar mission, nuclear thermal propulsion would reduce the Voyager equivalent travel time from 73,000 years to perhaps 30 to 40,000 years. Better. Still geological. Nuclear pulse propulsion goes much further. The concept, developed in the late 1950s under the classified American program known as Project Orion, proposed detonating a rapid series of nuclear or thermonuclear bombs behind a spacecraft, absorbing the force of each successive blast with a massive shock-absorbing plate called a pusher plate. The violence of the proposition is not metaphorical. The vehicle would ride a sequence of nuclear detonations, but the physics are not unreasonable. Freeman Dyson, one of the theoretical architects of the Orion concept, calculated that a sufficiently large Orion-class spacecraft could theoretically reach velocities on the order of 3 to 5% of the speed of light. At 5% of the speed of light, the crossing to Proxima Centauri would require approximately 85 years, less than a human lifetime. Still long, still requiring a crew with a multi-generational commitment or a radical life extension technology. But for the first time, a number that begins to feel like it occupies the same order of magnitude as a human life. Project Orion was ended by the Partial Nuclear Test Ban Treaty of 1963, which prohibited nuclear detonations in space. The engineering concept was never tested at scale. The physics remain valid. The political and environmental obstacles remain absolute. No serious contemporary effort to revive nuclear pulse propulsion exists. The next generation of theoretical proposals centers on nuclear fusion, the same process that powers the sun, in which light atomic nuclei are fused together to form heavier ones, releasing tremendous energy. A fusion-powered rocket could, in principle, achieve exhaust velocities far exceeding those of fission-based systems, potentially pushing a spacecraft to 10 or even 20% of the speed of light. At 20% of light speed, the crossing to Proxima Centauri takes 21 years, a single human generation, a plausible career, a conceivable mission duration. The fundamental problem is that controlled nuclear fusion, the sustained, contained harnessing of fusion reactions to produce net energy output, has been chased by physicists, let alone in a spacecraft. The landmark announcement in December 2022 by the National Ignition Facility at Lawrence Livermore National Laboratory, in which a fusion experiment produced more energy output than the laser energy delivered to the target, was genuinely significant as a scientific milestone. It was not, however, a demonstration of a practical power plant. The total energy efficiency of the laser system driving the experiment remained deeply negative. The path from that proof of concept to a fusion drive capable of accelerating a spacecraft to a meaningful fraction of light speed passes through engineering challenges of a scope and duration that no one can currently estimate with confidence. And then there is breakthrough starshot. In April 2016, the physicist Stephen Hawking and the technology entrepreneur Yuri Milner stood together in New York and announced an initiative that was genuinely unlike anything previously proposed in the public forum of spaceflight planning. They called it Breakthrough Starshot. The core concept was elegant in its audacity. Rather than accelerating a large spacecraft with a powerful engine, the proposal reversed the problem entirely. Make the spacecraft so small gram-scale, postage stamp-sized, that it requires only a modest amount of energy to accelerate, and deliver that energy not through an onboard propulsion system, but through an external source, an enormous phased array of ground-based lasers, focusing coherent light onto a reflective sail attached to the tiny spacecraft. The sail, catching the laser beam, would be pushed by the photon pressure of the light itself. No fuel required, no reaction mass, just a sail and light. The mathematics of this concept, applied to the parameters Milner and Hawking announced, produce a number that still stops conversations. The proposed laser array would deliver a power output on the order of 100 gigawatts, roughly equivalent to the total electricity generating capacity of the entire United Kingdom, focused for a brief period on a sail, few meters across, carrying a chip-sized spacecraft weighing perhaps a single gram. Under this bombardment, the sail and its payload would accelerate to approximately 20% of the speed of light within a matter of minutes. 20% of light speed. The crossing to Proxima Centauri, approximately 20 years. The proposal was not science fiction in the sense of violating physical law. The components in principle are all physically permitted. Laser arrays exist. Light sails have been demonstrated, albeit at far more modest scales. The Japanese Icaro spacecraft deployed a solar sail in 2010 and was pushed by solar photon pressure. Miniaturized spacecraft, the mass of a few grams, are not exotic. The challenge is the assembly of these elements at the scale required and the engineering problems that scale introduces. 100 gigawatts of coherent, precisely aimed laser power has no precedent in human technology. The largest laser systems currently in existence operate at a tiny fraction of that output. Constructing a phased array of the required scale, maintaining the optical coherence necessary to keep the beam focused on a sail, moving away at increasing velocity, managing the thermal load on the mirror surfaces, developing a sail material that can survive the intensity of that beam without vaporizing. Each of these challenges represents a research program of substantial depth and duration. The chip-scale spacecraft must survive the acceleration 20,000 times the force of Earth's gravity, and must then function for 20 years in the radiation environment of interstellar space before encountering the Proxima system and transmitting data home. Breakthrough Starshot attracted serious scientific attention. Peer-reviewed papers examined the beam formation problem, the sail material requirements, the miniaturization challenges. A formal research program was established. Funded science was conducted. The initiative was not a press release in search of substance. And then, quietly, it stalled. The engineering gaps proved wider than initial enthusiasm suggested. The development timeline for a laser array of the required scale extended far beyond what early projections had implied. The materials science challenges of building a sail that survives the beam intensity at the proposed power levels remained unresolved. By 2025, Breakthrough Starshot had entered what its own organizational communications acknowledged was a period of reassessment. The project did not announce cancellation, it announced a pause. The distinction may be real, or it may be the language organizations use when ambitions have collided with the full weight of the underlying technical obstacles and the outcome is not yet clear. The pause is honest, the challenges are real, and the 20-year crossing time that the concept promised is still a goal, not an achievement. A gram-scale chip with a camera and a transmitter, traveling at 20% of light speed, would face an additional problem that no amount of engineering finesse can eliminate. The data it returns would travel 4.24 years to reach Earth, arriving as radio signals so faint, coming from so far, that receiving them would require ground-based antennas of extraordinary sensitivity. And the spacecraft itself, a chip traveling at 1/5 the speed of light, would pass through the Proxima system in a matter of hours, with no capacity to decelerate, no capacity to enter orbit, no capacity to linger, a flyby, a brief, blinding encounter, during which sensors would record whatever they could before the system fell behind and the darkness closed back in. Not a landing, not a colony, not a presence. A photograph taken while falling through at 1/5 of the speed of light, transmitted 4 years later to a civilization on a planet the photographer will never see again. That is Breakthrough Starshot at its most optimistic. That is the best current proposal for sending anything to the nearest star. A gram, a sail, a chip, a flyby, and a 4-year wait for a signal that may or may not survive the crossing. Nothing in this accounting changes the distance. Nothing in this accounting changes the physics. The fastest machine we have ever built needs 6,000 years. The most ambitious proposal ever seriously funded by a multi-hundred-million-dollar initiative promises 20 years for a chip. Every solution to the speed problem, examined with honesty, reveals the same underlying structure. The more seriously you try to solve it, the more precisely you understand the scale of what remains unsolved. The distance does not shrink. It simply becomes more clearly itself, 24.9 trillion miles of vacuum, exactly as wide as it has always been. And all of this has so far concerned only unmanned probes, chips, grams, postage stamps flung across the dark. We have not yet addressed what happens when the thing being sent is not a gram of circuitry on a light sail, but a human being. That is where the accounting becomes truly merciless. There is a mathematical object at the heart of rocketry that engineers treat with a kind of reverence bordering on resignation. It is called the Tsiolkovsky rocket equation, named after the Russian schoolteacher and self-taught theorist Konstantin Tsiolkovsky, who derived it in 1903 while working in near-complete obscurity in the town of Kaluga, roughly 110 miles southwest of Moscow. Tsiolkovsky had no laboratory, no institutional affiliation, no colleagues engaged in the same work. He was a nearly deaf schoolteacher who spent his evenings and weekends filling notebooks with calculations about the physics of space travel, decades before anyone had built a rocket capable of reaching the upper atmosphere, decades before the concept of orbital mechanics had entered mainstream scientific discourse. His rocket equation, when applied to the demands of interstellar travel, produces numbers so catastrophic that they function less like engineering parameters and more like a formal mathematical proof that human beings are not meant to make this crossing. The equation states, with elegant simplicity, that the ratio of a rocket's initial mass to its final mass, the mass at launch divided by the mass after all propellant has been expended, must equal a specific exponential function of the desired velocity divided by the fecting the day exhaust velocity of the propulsion system. The exponential is the cruelty. Every time you increase the desired final velocity, the required propellant mass does not increase proportionally, it increases exponentially. For small velocity changes, the equation is manageable. For the velocity changes required to accelerate a crewed spacecraft to a meaningful fraction of the speed of light, and then decelerate it again at the destination, so the crew does not simply fly through the Proxima system in a flash and continue into the void, the equation stops being manageable and becomes a statement about what is physically achievable with matter. Consider a relatively modest ambition, a crewed mission to Proxima Centauri carrying 50 people, traveling at 10% of the speed of light, a velocity that would make the crossing in approximately 42 years using a theoretical fusion drive, achieving exhaust velocities at the upper end of what fusion physics permits. The spacecraft must accelerate to 10% of light speed in the first half of the journey and decelerate back to near zero relative velocity in the second half, so the crew can actually arrive rather than pass through. The mass of the crew, their life support systems, their food, their water recycling equipment, their medical facilities, their radiation shielding, their communications hardware, and all the other infrastructure required to keep 50 human beings alive for 42 years in deep space has been estimated by various engineering analyses to sit in the range of several thousand metric tons at minimum, and that is before you calculate the propellant. When the rocket equation is applied to this scenario, 50 people, 42 years, fusion propulsion, acceleration and deceleration, the required propellant mass is approximately 68.5 million metric tons. 68.5 million metric tons of fusion fuel to deliver a crewed spacecraft carrying 50 people to Proxima Centauri at 10% of light speed. For context, the total mass of every rocket ever launched by humanity from the surface of the Earth across the entire history of spaceflight is approximately a few tens of thousands of metric tons. The propellant requirement for a single crewed interstellar mission to the nearest star exceeds the total launch mass of all of human spaceflight history by a factor of several thousand. The fuel alone would weigh roughly 800 times as much as the Great Pyramid of Giza. It would outmass the entire steel production of the United States across several years of peak industrial output. And that number assumes fusion propulsion, a technology that does not exist in operational form. If you step back to the best currently demonstrated propulsion, the propellant requirement does not merely increase. It becomes cosmological. It becomes a number that exceeds the mass of moons and approaches the mass of small planets. The rocket equation applied to chemical propulsion at interstellar velocities does not produce a difficult engineering challenge. It produces a mathematical impossibility, a propellant mass so large that no plausible structure could contain it, no plausible gravity well could assemble it, no plausible manufacturing base could produce it before the Sun completes a measurable fraction of its own orbit around the galactic center. This is not a temporary obstacle waiting for a clever engineer to solve it with a new material or a better manufacturing process. The exponential function at the heart of the rocket equation is a statement about the physics of momentum, not a statement about the limits of current technology. You cannot engineer your way around an exponent. You cannot prototype a solution to an exponential relationship and then scale it down with better machining tolerances. The equation is exact. The exponent is real, and the numbers it produces, applied to crude interstellar travel, are not large in the way that ambitious engineering projects are large. They are large in the way that violations of physical law are large. They are the mathematics of impossibility dressed in units of metric tons. But suppose you sidestep the rocket equation entirely. Suppose you commit to a different framework, not a ship that carries its own fuel, but a ship that has already been accelerated by some external mechanism, a laser array like Starshot, or a mass driver, or some future technology that delivers the required velocity without requiring the vehicle to carry its own propellant. The rocket equation problem disappears. The mass budget becomes manageable. Suddenly, the conversation about crude interstellar travel can proceed in engineering terms rather than in the language of mathematical catastrophe. What then? What does a crude vessel actually need to sustain 50 human beings for 42 years in the void between stars? The first answer is a closed ecological system, a vessel that cannot resupply from Earth, that will not reach its destination for decades, must be internally self-sufficient in every material sense. The air the crew breathes must be regenerated continuously. The water they drink must be recycled completely. The food they eat must be grown aboard the vessel, which means light sources for photosynthesis, soil or hydroponic medium, agricultural knowledge, crop varieties selected for yield and nutritional completeness in artificial environments. The waste they produce must be composted or chemically processed back into nutrients. The entire metabolic cycle of a small human community must close within the volume of the ship, with no net loss of any essential element, sustained across 4 decades. There is a test case for this ambition. It did not go well. Biosphere 2 was built in the desert north of Tucson, Arizona, between 1987 and 1991, a sealed glass and steel structure covering approximately 3 acres, containing several distinct biomes including a miniature rainforest, a fog desert, a grassland savanna, a freshwater marsh, a saltwater ocean, and an agricultural area intended to support a resident crew of 8. The project was funded by the billionaire Ed Bass at a cost exceeding $200 million, designed by a team that included serious ecologists, engineers, and systems designers. The intention was to demonstrate that a closed biological system, a miniature Earth sealed inside glass, could sustain human life indefinitely without material input from the outside. The name referenced Earth itself as Biosphere 1. In September 1991, 8 crew members entered the structure and sealed themselves inside. The mission was intended to last 2 years. The problems began almost immediately and accelerated. Oxygen levels inside the structure began declining from the moment of sealing, a consequence of microbial activity in the soil that consumed oxygen faster than the plants could replenish it. Within 16 months, oxygen had dropped from its normal atmospheric concentration of 21% to to 14%, equivalent to the oxygen availability at an altitude of approximately 13,000 feet, the threshold where altitude sickness becomes a serious concern. The crew experienced fatigue, impaired cognition, and difficulty maintaining physical performance. External oxygen had to be pumped in. The sealed system had not sealed. The food situation was equally troubled. Crop yields fell below projections. Due to lower than expected light levels, the glass structure filtered out a significant portion of the solar spectrum, and the agricultural area could not produce sufficient calories. Crew members lost an average of about 16% of their body weight over the 2-year period. Food that had been stored as emergency reserves was quietly consumed. The agricultural system that was supposed to demonstrate the viability of a closed food supply could not sustain 8 people without supplementation. Animal extinctions cascaded through the enclosed ecosystem. Most of the vertebrate species introduced into the system died. Pollinating insects vanished, collapsing the reproductive cycles of plant species that depended on them. Ant species and cockroaches, meanwhile, proliferated beyond control. The ecological balance that had been carefully designed shattered within months into a configuration that no one had predicted and that resisted every corrective intervention. Interpersonal relations between the 8 crew members fractured badly. The group divided into factions that stopped communicating. Arguments over food allocation, over mission priorities, over the management of the deteriorating systems became corrosive. By the end of the first year, the 8 people sealed inside this glass structure in the Arizona desert were, by multiple accounts, barely speaking to each other across the team divide. Social cohesion, the substrate on which every collective survival effort depends, had dissolved. Biosphere 2 cost more than $200 million, employed teams of experienced ecologists and engineers, had 3 acres of carefully designed habitat, received natural sunlight through glass panels across that entire area, and sat a few miles from a support infrastructure that could intervene when the system failed, and it could not reliably sustain 8 people for 2 years. A crude interstellar vessel would need to sustain 50 to several hundred people for 40 to 80 years. It would receive no sunlight. It would be operating in the absolute darkness between stars, dependent entirely on artificial power sources for every photon that drove every photosynthetic reaction in every agricultural bay. It would be genuinely sealed, no external intervention possible, no supply mission that could close the distance in time to matter, no technician who could fly out to address a cascading failure before it became irreversible. And it would need to maintain not just basic survival, but the psychological coherence, the social stability, the institutional continuity, and the technical expertise required to operate a spacecraft of extraordinary complexity across timescales that no human institution has ever maintained cohesion through. The human body presents its own separate accounting. The physiological effects of prolonged spaceflight on human biology have been documented with increasing precision as astronauts have spent longer durations aboard the International Space Station. The record for continuous time in space is held by the Russian cosmonaut Oleg Kononenko, who surpassed 1,000 days in orbit across multiple missions. The data accumulated from long-duration ISS missions, and particularly from NASA's Twin study, in which astronaut Scott Kelly spent a year in orbit, while his identical twin brother Mark remained on Earth. Providing a controlled comparison has produced a detailed map of what microgravity and space radiation do to the human body across timescales measured in months to a year. The results are not reassuring extrapolated to decades. Bone density declines at a rate of approximately 1 to 2% per month in the load-bearing bones of the lower body, despite rigorous daily exercise countermeasures. The loss can be partially recovered after return to Earth, but the recovery is incomplete and becomes progressively less complete with longer exposure. Muscle mass declines in parallel. Cardiovascular fitness deteriorates as the heart adapts to a fluid distribution environment in which it no longer needs to pump blood against the force of gravity. Fluid shifts toward the upper body compress the optic nerve, causing a condition called spaceflight-associated neuro-ocular syndrome, structural changes in the eye that cause vision impairment in a significant fraction of long-duration astronauts. The immune system exhibits dysregulation, gut microbiome composition shifts. Epigenetic changes modifications to the way genes are expressed, without altering the underlying DNA sequence, accumulate in ways that are not yet fully understood. All of these effects occur aboard the International Space Station, which sits in low Earth orbit approximately 250 miles above the surface, within the partial protection of Earth's magnetosphere, at a radiation level already elevated compared to the surface, but far below what would be experienced in deep interstellar space. The mitigation strategies currently available: exercise equipment, medication, dietary supplementation, monitoring are developed and refined continuously by teams of flight surgeons who can communicate with the crew in real time and provide updated medical protocols within seconds. On an interstellar vessel, communications with Earth operate at light speed. At the distance of Proxima Centauri, a transmission takes 4.24 years each way. A crew member who develops a medical emergency cannot consult with Earth-based physicians in real time. By the time a distress signal reaches Earth and a response is transmitted back, 8 years have passed. The crew must contain within itself the complete medical knowledge and surgical capability required to address every foreseeable health crisis, and some that are not foreseeable across 40+ years, in an environment of elevated radiation, reduced gravity, social confinement, and psychological stress that has no equivalent in human history. Radiation deserves its own careful accounting. The two primary radiation threats in deep interstellar space are solar energetic particles, intense bursts of charged particles released during solar flare and coronal mass ejection events, and galactic cosmic rays, which are high-energy atomic nuclei accelerated to near light speed by supernova remnants and other energetic astrophysical sources distributed throughout the galaxy. Solar energetic particles can be partially addressed by shielding and by staying within the protective envelope of a planetary magnetic field, but an interstellar vessel is not within any such field. Galactic cosmic rays are the more insidious threat. They arrive from all directions continuously, carry sufficient energy to penetrate even substantial shielding, and include heavy ions, the nuclei of iron, silicon, and other heavy elements that are particularly destructive to biological tissue because they deposit their energy in dense ionization tracts rather than diffuse clouds. Heavy ion radiation passing through human tissue does not merely kill cells in bulk. It damages them in patterns that chemical repair mechanisms struggle to address, creating complex double-strand breaks in DNA that the cell's repair machinery cannot always correctly fix. The resulting mutations accumulate. The risk of cancer, neurological damage, and systemic cellular dysfunction compounds with exposure time. NASA's current regulatory limit for career radiation exposure for astronauts, a limit that has been revised upward over time but remains constrained by cancer risk estimates, would be exceeded in the first few years of an interstellar crossing conducted without substantially more shielding than any currently proposed vehicle design incorporates. Shielding helps. Mass stops radiation, but mass is exactly what every interstellar propulsion concept most desperately needs to minimize, because every additional kilogram of shielding is another kilogram that must be accelerated to a significant fraction of the speed of light, multiplying the propellant requirement through precisely the exponential relationship that makes the rocket equation so merciless. The engineering optimization of an interstellar crewed vessel is a negotiation between two demands that move in opposite directions. More shielding protects the crew but increases mass, and more mass increases the energy requirement and the propellant load without bound. There is no clean resolution to this tension in any currently published engineering analysis. There is parameter space, and there are trade-offs, and there are design choices that shift the balance one direction or another. But the tension itself, the structural conflict between the biological requirements of long-duration human spaceflight and the propulsion physics of getting anywhere meaningful in a reasonable time, does not dissolve. It is not an engineering problem awaiting a clever solution. It is a statement about the mismatch between human biological fragility and the environment of interstellar space. The human body was not built for this. It was built by 4 billion years of evolution on a rocky planet with a robust magnetic field, a thick radiation-absorbing atmosphere, one gravity surface acceleration, a 24-hour day-night cycle, a broad ecosystem of microbial companions, and a stable social environment in which cooperative groups of dozens to a few hundred individuals managed resources and navigated threats. Every single one of those conditions is absent in deep interstellar space. The adaptation required is not the kind of adaptation that can be achieved through training, exercise, and dietary supplements over the 6 months an astronaut spends preparing for an ISS mission. It is adaptation at a scale and depth that training cannot touch. And yet, the distances do not care. The physics does not revise itself to accommodate biology. The 42 years of crossing at 10% of light speed are 42 years, regardless of what they do to the crew. The void does not compress for the sake of human endurance. It simply stretches on, the same 24.9 trillion miles it has always been, and waits for something durable enough to cross it. Whether anything human is durable enough is a question the next part of this journey must answer. Because we have not yet confronted the dimension that may ultimately prove the most devastating barrier of all. Not the distance, not the propulsion, not the biology, but what happens to the mind and to human society when the crossing is so long that the people who arrive are not the same people who left. Imagine a vessel moving at 10% of the speed of light. That is approximately 67 million miles per hour. At that velocity, the ship is covering a distance equal to the circumference of the Earth every single second. It is crossing the gap between the Earth and the Moon in roughly 13 seconds. It is departing the orbital distance of Mars in less than 3 minutes. The number feels like speed. It feels, for the first time in this entire accounting, like something that might actually work, a velocity that compresses the void, that turns the incomprehensible into the merely extraordinary. And then you ask what the vessel is flying through, and the answer reassembles the dread. Interstellar space is not empty. This is one of the most consequential misunderstandings embedded in the popular image of spaceflight. The phrase empty space appears so frequently in casual descriptions of the cosmos that its inaccuracy has become invisible. Space is not empty. It is filled with the interstellar medium, a diffuse but real material environment consisting of gas, primarily hydrogen and helium in various ionization states, along with trace amounts of heavier elements, complex molecules, and micron-scale dust grains composed of silicates, carbonaceous compounds, and ice. The density of this medium is extraordinarily low by any standard of human experience. In the denser regions of the interstellar medium, the particle density is roughly 1 atom per cubic centimeter. In a cubic centimeter of air at sea level on Earth, there are approximately 27 million trillion atoms. The interstellar medium is, by any reasonable everyday standard, almost incomprehensibly sparse. Almost, but not to a spacecraft traveling at 10% of the speed of light. At that velocity, the kinetic energy of even a single interstellar dust grain, a particle perhaps 1/10 of a micron across, smaller than a bacterium, invisible to any unaided sense, is calculated at approximately 1 kilojoule. 1 kilojoule sounds modest. It is roughly the energy contained in 1/4 of a calorie, the kind of energy budget you might associate with a small bite of food. But kinetic energy is directional, concentrated, and deposited instantaneously at the point of impact. 1 kilojoule delivered in a microsecond to a surface area measured in microns is not food, it is a crater. At higher velocities, 20% of light speed, as Breakthrough Starshot proposes for its sail, the kinetic energy of dust grain impacts scales with the square of the velocity, quadrupling for a doubling of speed. A 1-micron silicate particle strikes the leading surface of a vessel traveling at 20% of light speed with the energy of a small explosive charge. The interstellar medium is not empty. It is a shooting gallery in which every projectile is invisible and every impact occurs without warning. The engineering response to this threat is to design the leading surface of any interstellar vessel, the bow, the shield, the first material that meets the oncoming flow of particles from materials hard and thick enough to survive continuous micro-impact damage across the duration of the crossing. This requires mass. It requires substantial mass, deployed as a sacrificial shield at the front of the vessel, designed to ablate slowly as the particle flux erodes it grain by grain, atom by atom, across 40+ years of continuous bombardment. The shield must be thick enough that it retains protective function at journey's end, having been progressively consumed from its leading face throughout. Calculating the required initial shield thickness demands a precise model of the interstellar medium along the specific trajectory, a quantity that is not uniformly known and that includes local variations, denser clouds, thinner voids that may not be measurable from Earth with sufficient resolution to plan around. Project Daedalus, a detailed interstellar probe design study conducted by the British Interplanetary Society between 1973 and 1978, examined this problem with engineering rigor and concluded that a beryllium-copper erosion shield, several millimeters thick, would be required at the nose of their proposed vehicle, which was designed for an unmanned flyby rather than a crewed mission. For a crewed vessel carrying people rather than instruments, the required shield mass increases substantially, both because the shielded area is larger and because the acceptable erosion rate must be far more conservative when human lives depend on the shield's integrity at journey's end. The shield adds mass. Mass adds to propellant requirements. Propellant requirements feed back through the rocket equation's exponential. Every solution generates a new constraint. But the individual impacts of micron-scale dust grains, dramatic as their accumulated effect may be, are not the most dangerous objects a relativistic spacecraft must contend with. They are the most numerous. They are not the most destructive. The interstellar medium also contains particles at larger scales, grains, tens of microns in diameter, perhaps larger, present in lower but still non-negligible concentrations along any trajectory spanning light years. A grain 100 microns across, a particle the size of a fine grain of sand, striking a spacecraft hull at 10% of light speed, deposits energy equivalent to a small artillery round. A millimeter-scale particle still too small to detect at interstellar distances with any currently conceived sensor would deliver an impact comparable to a substantial explosive charge, penetrating any realistic hull material and creating a catastrophic breach if it struck a pressurized section. The probability of encountering any given size of particle over a specific trajectory is calculable from the known grain-size distribution of interstellar dust, and the probability of encountering a millimeter-scale particle along a path 4 light-years long is small. It is not zero. The question a mission designer must answer is not whether the probability is low, but whether it is low enough, whether the mission can be morally justified given a finite, quantifiable probability of catastrophic hull failure at some point during a 40-year crossing from which no rescue is possible and no return is achievable. No supply mission could close the distance. No repair crew could be dispatched. No external intervention of any kind could affect the outcome of a catastrophic event in any time frame shorter than 4 years, by which point the event's survivors, if any, would long since have exhausted their capacity to respond. This is the environment's answer to the engineering question. The void between stars is not waiting with weapons aimed at the approaching vessel. It is simply being itself sparse, cold, particle-laden, and completely indifferent. The particles do not aim, they simply sit in the path at the concentrations they have always occupied, while the spacecraft approaches at velocities that transform their inert presence into a continuous, probabilistic, unintentioned bombardment. Beyond the particle environment lies the problem of time and mechanical degradation. 40 years of continuous operation for every system aboard the vessel, every pump cycling, every valve actuating, every seal maintaining its integrity, every filter processing its designated fluid stream, every bearing rotating, every sensor transmitting, every power connection conducting. The engineering discipline that addresses this reliability engineering, failure mode analysis, materials science under long-duration loading has produced extraordinary achievements in domains where 40-year component lifetimes are required. Nuclear power plants operate continuously for decades, Satellites in geosynchronous orbit function for 15 to 20 years without servicing. Certain industrial machinery runs for decades in continuous operation with only scheduled preventive maintenance. But every one of those examples involves a critical capability that an interstellar vessel lacks entirely: the ability to replace failed components. A nuclear power plant that develops a pump failure can be shut down, the pump replaced, and the plant restarted. A satellite that loses a component typically carries redundant backup systems, and when those fail, the satellite is decommissioned and replaced by a new launch. The industrial machinery can be serviced, parts can be fabricated on demand, engineers can be dispatched. Supply chains extend to the point of failure and deliver what is needed. An interstellar vessel in transit is beyond every supply chain that will ever exist in human history. No part can be delivered, no engineer can be dispatched, no component can be swapped from external stock. Every part that might fail over 40 years must either be present aboard the vessel at departure, multiplied by the redundancy factor, appropriate to its criticality, or must be manufacturable in situ from raw materials, fabrication equipment that are themselves subject to the same failure dynamics, requiring their own spare parts, their own redundancy margins, their own maintenance cycles. The inventory problem this creates is not trivial. Consider a single critical system, the water recycling plant that processes crew, urine, sweat, condensate, and grey water back into potable water. Current ISS water recovery systems achieve approximately 93 to 98% recovery efficiency, meaning that out of every 100 kilograms of water put into the system, 93 to 98 kilograms emerge as recoverable product. The remaining fraction is lost to inefficiencies in the processing chain. On a mission lasting 40 years with a crew of 50, the cumulative water throughput is enormous, and each percentage point of recovery efficiency represents hundreds of thousands of liters over the mission lifetime. The system contains pumps, membranes, ion exchange resins, catalytic oxidation reactors, sensors, valves, filters, and control electronics, each with its own mean time between failures, its own maintenance interval, its own replacement part requirement. Now multiply that analysis across every critical system aboard the vessel: life support, power generation and distribution, propulsion management, navigation and attitude control, communication systems, medical equipment, agricultural systems, computing infrastructure, structural monitoring, emergency systems. Each system contributes its own inventory of failure modes. Each failure mode requires its own spare part strategy, and the aggregate spare parts inventory begins consuming volume and mass in ways that feed back, again and again, into the mass budget that the rocket equation governs. The engineering term for the interaction between component failures in complex systems is cascade failure, a condition in which the failure of one component stresses adjacent systems in ways that increase their failure probability, potentially triggering a cascade of sequential failures that spreads through the vessel faster than the crew can diagnose and respond to each individual failure event. Space systems engineers design for cascade failure resistance through redundancy, isolation, and fault containment, ensuring that failures in one subsystem cannot propagate to adjacent ones. But cascade failure resistance itself adds mass, adds complexity, and introduces new potential failure modes in the isolation and switching systems designed to contain failures. No spacecraft of sufficient complexity to support 50 human beings for 40 years has ever been built. The International Space Station comes closest, but it has been continuously resupplied and partially rebuilt over its operational life. It has had components replaced, systems upgraded, and failed hardware returned to Earth for examination. It operates in low Earth orbit where rescue is a matter of hours and resupply is a matter of days. The failure modes experienced aboard the ISS over its more than 25 years of operation, cooling system leaks, toilet malfunctions, atmospheric contamination events, oxygen generation system failures, communications outage, fire suppression activations represent a partial catalogue of what an interstellar vessel would need to absorb and repair without external support across a mission 20 to 40 times longer. There is one more element of the physical environment that the instruments and the calculations cannot fully capture. One more dimension of the crossing that resists engineering optimization because it operates not through mechanisms but through meaning. An interstellar vessel traveling at 10% of the speed of light is a sealed container crossing an absolute void in which every signal from the civilization that built and launched it arrives with a delay that grows over the early years of the crossing, plateaus during the middle decades, and closes again as the destination approaches. At departure, the round-trip communication delay is negligible hours, then days. In the first year, it is measured in weeks. By year 5, messages from Earth take months to arrive. By year 21, at the halfway point of a 42-year crossing at 10% of light speed, when the vessel has covered approximately 2 light years, the one-way communication delay to Earth exceeds 2 years. A crew member who asks a question, reaches out for guidance, transmits a distress signal, or simply wants to hear a voice they know, waits more than 2 years for any response. By the time the vessel approaches Proxima Centauri, messages from Earth take more than 4 years each way, 8 years round trip. The people who launched the mission are, by then, very old or dead. The institutions that funded it have changed. The political environments that supported it may no longer exist. The specific engineers who designed the systems are retired. The cultural context that gave the mission its meaning, the specific moment in human history that decided this crossing was worth attempting, is 40 years in the past, from the perspective of the crew, and 40 years is long enough for civilizations to transform themselves beyond recognition. This is the loneliness that has no engineering solution. Every spacecraft that has ever left Earth has maintained communication with ground controllers in real time or near real time. Voyager 1, at its current distance, experiences a communication delay of approximately 22 hours each way, a long delay by the standards of human conversation, but still within the span of a single day. The crew of an interstellar vessel in its middle decades is separated from every human voice, every piece of news, every update from home by a gap measured in years. They are not explorers in radio contact with a distant base camp. They are something for which no adequate human analogy exists. They are a civilization small, sealed, alone that has severed every connection to the world that made it and accepted that the severing is permanent. The message that left Earth on the day of departure will take years to arrive. The response to that message will take years to return. By the time any meaningful exchange of information has completed a round trip, the world that sent it will have moved on, changed, perhaps forgotten. The crew does not receive news from home. They receive history. They receive dispatches from a past that recedes at the speed of light, while they advance at 10% of that speed, chasing a future that is still decades away. This isolation absolute, physics-enforced, non-negotiable is a condition that no training program, no psychological preparation, no mission architecture can fully address. It can be anticipated, it can be planned around, its effects can be studied in analog environments, but it cannot be eliminated because it is not a design flaw. It is a direct consequence of the distance and the speed of light. It is the cosmos imposing its terms on any living thing that dares to attempt the crossing, and the cosmos does not negotiate. In the summer of 2010, 6 men entered a steel cylinder in Moscow and sealed the hatch behind them. The facility was designed to simulate, as faithfully as possible without leaving Earth, the conditions of a crewed mission to Mars. The project was called Mars 500, organized jointly by the Russian Institute of Biomedical Problems and the European Space Agency, and it ran for 520 days, the approximate duration of a round trip to Mars, including surface time, based on the mission profiles then under consideration. The 6 participants lived inside an interconnected series of modules, with a total habitable volume of approximately 550 cubic meters, roughly the interior space of a modest suburban house. They conducted simulated experiments, maintained mock mission protocols, ate pre-packaged food, exercised on stationary equipment, and waited for the days to pass. 520 days, not 40 years, not the duration of an interstellar crossing. 520 days in a facility located within Moscow, attended by support teams who were physically present outside the hatch, in a simulation with no actual risk of death, no radiation, no mechanical failure, no genuine emergency, and no real communication delay. The simulated delay was imposed artificially on messages to and from the crew, but the crew knew with complete certainty that genuine help was a door's width away at all times. It was theater with real bodies inside it, and it produced results that the scientists running the experiment have described, with careful understatement, as sobering. The data from Mars 500 revealed a consistent and progressive deterioration in physical activity levels across the crew. Despite having exercise equipment and a mission protocol that explicitly scheduled daily physical conditioning, the crew's movement steadily declined as the mission extended. Sedentary time increased. By the final months of the simulation, certain crew members had reduced their activity to levels that, on Earth, would be associated with chronic health risks. The mission designers had anticipated that motivation might decline. They had not fully anticipated how early and how completely the environment would erode the will to maintain physical discipline, not through any single dramatic collapse, but through the accumulated weight of monotony, confinement, and the absence of any external sensory environment to engage the nervous system. Sleep disruption was pervasive. The crew's circadian rhythms, the internal biological clocks that regulate sleep, wakefulness, hormone secretion, metabolism, and cognitive function desynchronized progressively from the artificial day-night cycle imposed by the facility's lighting schedule. Individual crew members drifted into idiosyncratic sleep patterns that did not align with the mission schedule or with each other, creating a crew whose members were functioning in different biological time zones despite occupying the same physical space. The implications for coordinated emergency response, the scenario in which every crew member must be alert, coherent, and effective simultaneously, were not comfortable. Psychological assessment throughout the mission documented increasing social withdrawal among individual crew members, a progressive disengagement from the structured mission activities, and a general flattening of emotional affect that the researchers characterized as behavioral torpor. The crew were not, for the most part, acutely distressed. They were not experiencing breakdowns or acute psychiatric crises. They were doing something subtler and in some respects more worrying. They were slowly retreating from engagement with their environment, their mission, and each other. Not dramatically, not irrecoverably, but measurably, progressively, and in ways that correlated with the duration of confinement. 520 days, in a steel cylinder in Moscow, with the door a few feet away. Now attempt to extrapolate that data across 40 years of genuine interstellar transit. Not a simulation, not a facility with support staff outside the hatch. A vessel that is genuinely, absolutely alone. A vessel from which the crew cannot leave, cannot be extracted, cannot be replaced. A vessel in which every one of the psychological processes documented in Mars 500, the sedentary drift, the circadian desynchronization, the social withdrawal, the behavioral torpor operates across a timescale, not of months, but of decades, in an environment with real radiation, real mechanical failure probability, real communication delays measured in years, and real consequences for every failure of discipline, every lapse of attention, every erosion of the social cohesion that holds the crew together. The International Space Station provides additional data points accumulated across more than 2.5 decades of continuous human occupation. Astronauts returning from 6-month ISS missions routinely report a period of readjustment to Earth's sensory environment. The sounds of wind and rain, which most humans tune out within minutes of exposure, can feel startlingly vivid after months in the acoustic uniformity of a spacecraft cabin. The smell of outdoor air complex, organic, shifting registers as intensely, almost overwhelmingly rich after the flat, processed air of the station. The proprioceptive experience of walking on solid ground under consistent gravity requires conscious attention for days or weeks after landing. The perceptual world of Earth, with its endless variability, its unpredictable sensory inputs, its constant low-level novelty, is something the human nervous system was built to inhabit. The spacecraft environment strips that novelty away completely and replaces it with a controlled sameness that conserves resources and maintains safety, but slowly starves the sensory and cognitive systems of the stimulation they require. 6 months produces perceptual readjustment lasting days to weeks. 12 months, the duration of Scott Kelly's year-long mission, produces effects that persist for months. The trajectory is not linear and not well characterized beyond approximately 14 months of continuous exposure. No human being has spent multiple consecutive years in deep space, and the data required to model what 40 years of spacecraft confinement would do to the human perceptual, cognitive, and social nervous systems simply does not exist. The models must extrapolate into territory where the extrapolation itself may be invalid, where the assumption that effects scale predictably from months to years to decades may be profoundly wrong in either direction. The question of generational ships vessels, designed not for a single crew to complete the crossing within their own lifetimes, but for the crossing to extend across multiple human generations, with crew members being born, living their entire lives, and dying aboard the vessel before it reaches its destination, introduces a new category of problem that goes beyond physiology and psychology into territory that is simultaneously ethical, anthropological, and existential. The baseline arithmetic of a generational ship depends on the assumed speed. At 1% of the speed of light, a velocity somewhat more aggressive than anything currently achievable, but less demanding than the relativistic crossings discussed in terms of propulsion, the journey to Proxima Centauri would require approximately 420 years. At 0.5% of light speed, the crossing extends to nearly 900 years. These are the timescales relevant to the kind of nuclear propulsion concepts that are within the outer range of foreseeable technological development without requiring the full fusion breakthrough. 400 years, 900 years, 15 to 35 human generations. The first and most fundamental ethical challenge of the generational ship concept is the question of consent. The initial crew of a generational vessel, the first generation, the people who chose to board and depart, can be said, with some qualification, to have consented to the journey. They were adults, presumably, who understood the nature of the undertaking and accepted its terms. Their decision was made freely, in whatever sense any human decision made under the full weight of institutional pressure, cultural expectation, and psychological complexity is free. Their children did not consent. Their grandchildren did not consent. The generation that actually arrives at Proxima Centauri, if the vessel survives the crossing and the mission succeeds, was born into a sealed metal environment that they never chose, raised by a culture that formed entirely within that environment, educated in the priorities and values and technical knowledge required to maintain the vessel, and never offered any alternative. They did not choose the crossing. The crossing chose them, in the same way that geography chooses the people born into it, except that geography allows for emigration and the vessel does not. The philosopher Bernard Williams wrote extensively about the concept of integrity, the idea that a person's deep commitments and projects constitute the core of their identity, and that to be forced to abandon those commitments is not merely an inconvenience, but a form of violation against the self. The generation born aboard an interstellar vessel and raised to be its maintenance crew has no access to the commitments, the projects, the possibilities, the landscapes, the relationships, or the freedoms that define human flourishing as it has been understood across the entire history of our species. They live in a bounded world of several thousand cubic meters. They breathe recycled air. They eat food grown under artificial light. They know Earth only as data, as stories, as cultural memory transmitted through the generations, with the inevitable distortions that transmission across decades introduces. Is this a life worth living? That question does not have an obvious answer, and the certainty with which different people reach different conclusions about it says more about their priors than about the lives of those hypothetical people. But the question itself must be asked, and asked honestly, before any civilization decides to build a vessel and fill it with human beings who will never be able to leave. Anthropology offers an unsettling perspective on what happens to isolated human communities over multi-generational timescales. The history of isolated populations on Earth, small island communities, valleys cut off by geography, colonial settlements that lost contact with their parent civilizations, provides a partial laboratory for studying cultural and social evolution under conditions of enforced separation. The results are consistent enough to constitute a pattern. Isolated communities drift. They drift linguistically, as vocabulary and grammar evolve along trajectories that diverge from the parent language without external correction. They drift culturally, as the specific practices and values that the founding population brought with them are modified, reinterpreted, and sometimes inverted by succeeding generations, responding to the pressures and circumstances of their specific environment. They drift technologically, as knowledge that is not continuously practiced and transmitted begins to erode. Skills that are not used become skills that are forgotten, and skills that are forgotten may not be recoverable from written records alone if the people reading those records have lost the experiential context that gives the records meaning. A generational vessel must maintain extraordinary technical competence across every generation. It must preserve the complete engineering knowledge required to operate and repair systems of enormous complexity. It must transmit that knowledge not as historical information, but as living, practiced skill, maintained at sufficient depth that any failure in any system can be correctly diagnosed and repaired by the crew that encounters it, which may be a crew several generations removed from the engineers who designed the system. Technical knowledge is not passive. It is not preserved simply by recording it. It requires practitioners, people who use it regularly, who test it against real problems, who develop the intuitions that come only from direct engagement with the underlying physical and mechanical reality. Small, isolated communities are generally not good at this. The history of isolated human populations is not primarily a history of preserved technical sophistication. It is a history of adaptation, simplification, and sometimes dramatic reduction of the technical complexity that the founding population brought. The skills and knowledge that survive are those that are immediately useful and repeatedly practiced. Skills that are complex, abstract, or relevant only to specific failure scenarios. The scenario where a particular pump in a particular system fails in a particular way may not be practiced often enough to survive as living competence across 15 or 20 generations without a deliberate institutional framework designed to force regular engagement with the full technical inventory. That institutional framework must itself persist across 15 or 20 generations. It must maintain its purpose, its authority, its structure, and its relationship to the technical knowledge it exists to transmit across a span of time equal to or exceeding the entire recorded history of Western civilization. No human institution has managed this. The Catholic Church, among the longest-lived institutional structures in Western history, has existed for approximately 2,000 years and has undergone transformations profound enough that its 3rd century founding members would find its 21st century form nearly unrecognizable. Nation-states typically survive a few centuries before dissolution, conquest, transformation, or revolution renders their institutional continuity a matter of historical debate. Universities, among the most enduring knowledge preservation institutions humanity has built, are generally measured in centuries rather than millennia, and even the oldest of them bear only a superficial resemblance to their medieval predecessors. A generational ship that must transmit complete technical knowledge across 900 years, 30 to 35 generations without external input, without the possibility of institutional renewal from outside, without the corrective pressure of contact with other knowledge traditions, is being asked to accomplish something that no human institution has ever managed in the full presence of civilization, culture, and external contact. The isolation does not help. The closure does not preserve. The sealed environment, without the continuous friction of contact with the larger world, removes the selection pressure that forces institutions to maintain relevance and adapt. There is a specific failure mode for knowledge in isolated communities that deserves its own moment of consideration. It is not the dramatic failure, the catastrophic loss of all records in a single destructive event. It is the quiet failure, the gradual failure, the failure that looks, from the inside, like continuity until it is too late. Consider a generation born aboard the vessel roughly 150 years into the crossing. They have been raised on the stories and technical manuals and cultural frameworks of the founders. They know, in an intellectual sense, everything about Earth that their parents and grandparents transmitted to them. They know that the vessel was built on a planet with vast oceans and open skies, that it was launched by people who could walk outside, that their destination is a star system that contains a potentially habitable world. They know all of this as information. They have never experienced any of it. For this generation, the vessel is not the means to an end. It is simply the world. It is all the world they have ever known or can viscerally imagine. The destination Proxima Centauri b, a planet that may or may not be habitable, that will not be reached for another 250 years, is not a real place in any experiential sense. It is a story, a destination that their great-great-grandchildren might reach. If the mission succeeds, if the vessel holds together, if the knowledge is successfully transmitted, if the institutional framework maintains its coherence. Now ask what motivation this generation has to maintain the discipline, the sacrifice, and the institutional commitment required to keep the mission on track. They did not choose the mission. They will not benefit from its completion. They are the middle of something that began before they were born and will end after they die. Their lives are entirely defined by being in transit, not at the origin, not at the destination, but in the void between, with no experiential connection to either endpoint. The philosophical and psychological literature on meaning and motivation suggests, fairly consistently, that human beings require a felt connection between their efforts and their outcomes. The delay between action and consequence that a generational mission imposes centuries of delay, experienced not as a delay at all, but as the entirety of reality is a condition for which human motivational psychology is not designed, and for which no known cultural framework has proven adequate across the required team scales. Yet for all of this, the biology, the engineering, the psychology, the anthropology, the ethics of consent, the institutional fragility, the motivational collapse across generations, there is still one more dimension of the crossing that has not yet been examined. A dimension that, for all the physical and human obstacles enumerated so far, may be the most quietly devastating of all. Because everything discussed in this accounting has treated the crossing as a matter of duration 40 years, or 400, or 900, measured in the clocks and calendars of the vessel and the civilization that launched it, but at the velocities required to make the crossing in any human-relevant time frame, duration is not a simple matter. Time itself becomes a variable, and the implications of that variability reach into the deepest layers of what it means to attempt this journey. That is where this story must now go. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published 4 papers in a single year that collectively restructured the foundations of physics. His name was Albert Einstein. The papers addressed Brownian motion, the photoelectric effect, special relativity, and the equivalence of mass and energy. He had no academic position. He had been rejected for a university assistantship after completing his degree. He reviewed patent applications by day and thought about the nature of light and motion in whatever hours remained. He was, by any conventional measure, nobody. And in that single year, working in near-complete institutional isolation, he dismantled the Newtonian framework that had governed physics for more than 2 centuries and replaced it with something that the majority of his contemporaries found, initially, almost impossible to accept. The special theory of relativity began with a deceptively simple premise. The speed of light in a vacuum is constant the same for every observer, regardless of their velocity relative to the source of the light. This postulate, combined with the principle that the laws of physics are the same in all inertial reference frames, generates a set of consequences that are mathematically elegant, experimentally verified, to extraordinary precision, and profoundly deeply strange when applied to the experience of moving objects and the people inside them. One of those consequences is time dilation. And time dilation is where the prospect of interstellar travel acquires a new dimension of complexity, one that initially appears to offer relief, and then, examined carefully, reveals itself as something more ambiguous and more costly than it first appears. The principle is this: a clock moving relative to a stationary observer runs slow, not metaphorically slow, not slow in the sense of appearing slow from a distance. Physically, genuinely slow, the moving clock accumulates less elapsed time than the stationary clock over the same interval of the stationary observer's time. This is not an optical illusion. It is not a consequence of signal travel time. It is a fundamental feature of the geometry of space-time, verified repeatedly and with extraordinary precision by experiments ranging from atomic clocks flown on aircraft to the GPS satellite network, which must account for relativistic time differences to maintain its navigational accuracy. If the GPS system did not correct for time dilation, both the special relativistic effect from the satellite's orbital velocity and the general relativistic effect from their altitude in Earth's gravitational field, its position estimates would accumulate errors of several kilometers per day. The corrections are real, the effect is real. For a spacecraft traveling at a significant fraction of the speed of light, time dilation becomes substantial. The quantity that describes it is called the Lorentz factor, designated by the Greek letter gamma. It expresses the ratio of the time elapsed in the stationary frame, Earth's frame, in our case, to the time elapsed aboard the moving vessel. At 10% of the speed of light, the Lorentz factor is approximately 1.005, barely distinguishable from 1. The time dilation at 10% of light speed is less than 1%, essentially negligible. The crew that departs on a 42-year crossing at 10% of light speed experiences approximately 41 years and 9 months aboard the vessel, while 42 years pass on Earth. The difference is months, not years. Time dilation at this velocity offers almost no practical relief. At 50% of light speed, half the speed of light, the Lorentz factor rises to approximately 1.15. Earth time and ship time now diverge meaningfully. A crossing to Proxima Centauri at half light speed takes approximately 8.5 years of Earth time, but the crew experiences roughly 7.4 years. A meaningful compression, but not dramatic enough to transform the fundamental character of the journey. At 90% of light speed, the Lorentz factor reaches approximately 2.3. The crossing of 4.24 light years takes approximately 4.7 years of Earth time, but the crew experiences only about 2 years aboard the vessel. The compression becomes genuinely significant. A 2-year journey by the crew's experienced time to cover 4.24 light years of distance. Begin to feel the pull of the idea. At 99% of light speed, the Lorentz factor climbs to approximately 7.1 Earth time for the crossing, about 4.3 years. Crew experience time, roughly 7 months. At 99.99% of the speed of light, the Lorentz factor reaches approximately 71. The crossing takes just over 4 years of Earth time, but only about 3 weeks by the crew's clocks. At the most extreme velocities, fractions of a percent below the speed of light, the time dilation becomes almost arbitrarily large. In principle, a spacecraft moving close enough to light speed could cross the entire observable universe in a single human lifetime, as measured by clocks aboard the vessel, while billions of years pass on Earth. This is the hope that time dilation appears to offer, the gateway, the escape clause embedded in the physics. If you go fast enough, the universe shrinks to human scale. If you go fast enough, the 4 light years to Proxima Centauri will compress into days or weeks of experienced time. The biology stops mattering. The crew does not age significantly during a transit of weeks. The psychology stops mattering. No one has had time to develop behavioral torpor or social fracture. The generational ship problem dissolves entirely. Speed fast enough, and the cosmos accommodates human lifetimes. The question is, what does fast enough cost? The answer is where the escape clause closes. because the energy required to accelerate a macroscopic object to a significant fraction of the speed of light does not scale linearly with velocity. It does not even scale as a simple power law. It scales as the Lorentz factor itself, meaning the energy requirement climbs steeply as velocity approaches light speed and rises toward infinity as velocity approaches the ultimate limit. The closer you push to the speed of light, the harder each additional increment of velocity becomes, because the effective mass of the object, the inertial resistance it presents to further acceleration, increases with the Lorentz factor. To accelerate a 10,000 metric ton crude vessel to 90% of the speed of light requires a kinetic energy equivalent to approximately 10 to the 22nd power joules. That is 10 billion trillion joules. The total energy released by all nuclear weapons ever detonated in the history of human testing, every atmospheric test, every underground test, every device ever exploded, amounts to approximately 1.7 times 10 to the 17th power joules. The energy required to push this single vessel to 90% of light speed exceeds the total energy of all nuclear weapons ever tested by a factor of roughly 100,000. The global energy consumption of human civilization, all energy, across all uses, worldwide, is approximately 5 times 10 to the 20th power joules per year. Reaching 90% of light speed for a crewed mission requires approximately 20 years of the entire world's energy output, delivered with perfect efficiency, which is not achievable by any known technology. At 99% of light speed, the energy requirement increases by a factor of roughly 20 compared to 90%. At 99.9%, it increases by a further factor of about 10. At each decimal of additional nines, the energy price multiplies. The Lorentz factor, the very quantity that compresses time and makes the journey humane in duration, is also the quantity that makes the energy requirement diverge toward infinity. Time dilation is not a free gift from the physics. It is a feature of a regime that becomes energetically inaccessible long before it delivers the compression needed to make the crossing trivially brief. The practical ceiling for realistically proposed interstellar propulsion fusion drives, antimatter engines, laser sails at the proposed starshot parameters generally sits in the range of 10 to 20% of the speed of light. At those velocities, as the Lorentz factor calculation confirms, time dilation provides less than 1% compression. The crossing is still measured in decades by the crew's own clocks. The biology matters, the psychology matters, the generational implications matter. The time dilation that the physics offers at achievable velocities is not enough to change the character of the journey, and the time dilation that would change the character of the journey requires energies that no civilization currently within sight of physical possibility can access. There is a further dimension to time dilation that the hopeful framing consistently underweights. The compression of experience time for the crew comes at the cost of an expansion of elapsed time at the destination. A crew that travels at 99% of light speed and experiences a journey of a few months arrives to find that more than 4 years have passed at their destination. If the mission involves a return trip, an assumption that crewed exploration missions generally require, if the crew is expected to come back, the time dilation asymmetry becomes devastating. A round trip to Proxima Centauri at 99% of light speed, experienced by the crew as a few months out and a few months back, consumes more than 8.5 years of Earth time. The crew returns to a civilization 8.5 years older than when they left, having experienced a journey of months. At higher velocities, the asymmetry grows larger. A mission that lasts a year by the crew's clocks might see decades pass on Earth. The crew members who return are young. The colleagues they left behind are old or dead. The children they had before departure are grown adults with children of their own. The world that greeted them at launch is historical. This is the condition the physicist Paul Langevin described in 1911, and that has since been called the twin paradox, though it is not a paradox at all, but a genuine physical asymmetry arising from the different space-time paths traveled by the two parties. It has been verified experimentally, at small but measurable scales, using atomic clocks on aircraft and in satellites. The asymmetry is real. The relativistic traveler genuinely ages less. The cost of that reduced aging is permanent displacement from the timeline of everyone and everything left behind. The crew members who travel at near light speed to Proxima Centauri and return do not come back to their lives. They come back to the historical record of their lives. Their relationships are not paused. Their children have not waited. Their colleagues have not held their positions open. The world continues at its own rate, accumulating years and changes and deaths and births, while the travelers age slowly in their vessel and return to find themselves strangers in a civilization that remembers them as historical figures more than as friends and family. They are, in the precise sense of the term, temporal refugees, people displaced not by geography or political violence, but by the physics of their own velocity, exiled from their own timeline by the decision to move fast enough that time itself carried them forward, relative to everyone they knew. At lower velocities, the 10 to 20% of light speed that proposed propulsion technologies might achieve, the time dilation is too small to create significant temporal displacement. The crew ages normally. They return, if they return at all, only slightly younger than they would have been if they had stayed. At the velocities that create significant temporal compression, the 90 and 99% regimes, the displacement becomes profound. There is no middle ground that offers both meaningful time compression and modest temporal displacement. The physics does not offer a comfortable compromise between the traveler's clock and the civilization's clock. The faster you go, the more compressed your journey, and the more completely you depart the timeline of everyone who stayed behind. The mathematics of the energy requirements for relativistic flight deserve one final translation from abstraction into physical terms, because the numbers involved require the same kind of visceral anchoring that the distance itself required earlier in this journey. Consider a 10,000 metric ton crewed vessel, modest by the standards of what would actually be needed to sustain a crew for decades, but a useful reference mass, and the energy required to accelerate it to various fractions of light speed using a perfectly efficient antimatter drive, the most energetically dense propulsion concept permitted by known physics. Antimatter annihilates with ordinary matter to produce pure energy, with a mass-to-energy conversion efficiency of 100%, the theoretical maximum. Nothing in known physics extracts more energy per unit mass than matter-antimatter annihilation. An antimatter drive is the ceiling. It represents the best possible propulsion performance available within the framework of currently understood physics. To reach 10% of light speed with a 10,000 metric ton vessel using an antimatter drive, you need approximately 56 metric tons of antimatter. Current annual global production of antimatter, primarily antiprotons, produced in particle accelerators like those at CERN, amounts to approximately 15 nanograms. 1 nanogram is 1/1,000,000th of a gram. 56 metric tons is 56 million grams. The ratio of required antimatter to current annual production is approximately 4 times 10 to the 18th power. At current production rates, it would take roughly 4 billion years to manufacture the antimatter required to accelerate a single modest crewed vessel to 10% of light speed. The current age of the universe is 13.8 billion years. Current antimatter production rates would need to sustain themselves, without interruption, for a duration approximately 300 million times the current age of the universe to supply a single mission. This is not a near-term engineering challenge. This is a statement about the relationship between current human technological capability and the energy demands of relativistic flight. The gap is not bridgeable by incremental improvement. It is bridgeable only by a transformation in human civilization's relationship to energy production, so total and so fundamental that it belongs to the same category of conceptual leap as the gap between a Stone Age campfire and a nuclear reactor. Such transformations are not impossible in principle. The history of science and technology is a history of transformations that previous generations considered impossible in principle. The limits of human technological capability have been wrong before, repeatedly and dramatically, but they have never been wrong by a factor of 4 billion. They have never been wrong by an amount that requires humanity to effectively become a different kind of civilization. a Type 2 civilization in the Kardashev scale, one capable of harnessing the total energy output of its home star before the problem begins to yield. The Kardashev scale, proposed by the Soviet astrophysicist Nikolai Kardashev in 1964, classifies civilizations by their energy consumption. A Type I civilization controls all energy available on its home planet. A Type 2 controls all energy from its home star. A Type 3 controls all energy in its home galaxy. By Kardashev's original definitions, humanity is currently a Type 0 civilization. We have not yet achieved the energy mastery of a full Type 1. The energy requirements of meaningful relativistic spaceflight place the achievement firmly in Type 2 territory. We are not close to Type I. And yet, even this accounting, the crushing energy arithmetic, the temporal displacement, the biological limitations, the engineering impossibilities of closed ecological systems, and 40-year mechanical reliability, even all of this understates the final depth of the problem, because all of it concerns the physical dimension of the crossing. None of it has yet addressed the most quietly devastating element of what makes the journey to the nearest star terrifying in a way that transcends physics and engineering and enters the domain of what it means to be a human being choosing to leave. That is where this journey ends. Everything examined so far in this journey has been a problem of physics. The distance is a problem of geometry. The speed is a problem of propulsion. The biological degradation is a problem of physiology. The mechanical failures are problems of engineering. The psychological erosion is a problem of neuroscience and social dynamics. The energy requirements are problems of thermodynamics. These are all problems in the sense that science and engineering address quantifiable, analyzable, potentially reducible through research and development and the long, patient accumulation of human ingenuity. They are hard. Some of them may be hard beyond any foreseeable solution, but they are, at least, the kind of hard that scientific civilization knows how to approach. They can be measured, they can be modeled, they can be improved upon incrementally, if not solved completely. The final dimension of the journey to Proxima Centauri is not that kind of problem. It is not quantifiable. It does not yield to engineering. It cannot be modeled in a differential equation or addressed in a peer-reviewed paper. It belongs to the oldest and most persistent questions human beings have ever asked about the meaning of their own existence. And it may be the most honest answer to the question of why the nearest star is terrifying, not because of what the crossing requires you to endure, but because of what it requires you to leave. Consider what a departure from Earth actually means. Stripped of the abstraction that space travel tends to accumulate around itself, a human being boards a vessel and departs. The vessel accelerates out of the solar system, passes the orbit of Neptune within hours at relativistic speeds, crosses the heliopause within days, and enters the interstellar medium. The solar system, the entire volume of space that contains every object ever visited by a human being or a human spacecraft, every planet, every moon, every asteroid, every comet that any civilization has ever observed closely shrinks behind the vessel. Within weeks, the sun has dimmed to a bright star. Within months, it is indistinguishable from the other bright stars in the sky without careful optical search. Within a year, it has receded to a point of light not dramatically different in appearance from Sirius or Canopus or Vega, as seen from Earth. And on that point of light, everything is happening, right now, simultaneously, from the vessel's reference frame. A child is being born in a hospital in Lagos. A fisherman is hauling nets off the coast of Vietnam at dawn, the water cold and the light just breaking across the horizon. Snow is falling on a mountain range in Patagonia with no one to watch it settle. A piece of music is being played for the first time. In a concert hall or a small room or a recording studio, notes arranged in a sequence that has never existed before in the history of the universe. Somewhere, two people are sitting across a table from each other, and one of them is saying something that will change both their lives. Somewhere, a very old person is dying quietly, surrounded by people who love them, in a room full of afternoon light. All of this is happening on that point of light. All of it is moving away at the speed the vessel is moving, and more slowly than that, because the vessel's clock has already begun its slight divergence from Earth's clock, and the gap will grow as the decades pass. The crew can receive signals from that point of light. They can know, in the sense of receiving data, what is happening on the world they left. But what they receive is history. What arrived today left Earth 4 years ago. What they are receiving now describes a world that no longer exists in the form described, a world that has continued for 4 years beyond the moment the signal captures, changed and aged and lost and gained in ways the signal does not contain. The point of light is home, it is receding, and nothing about the physics of the crossing can change what that recession means to a human nervous system built over millions of years of evolution to be embedded in exactly the kind of place being left behind. This is not sentiment dressed as analysis. The relationship between human beings and their environments is not peripheral to human psychology. It is constitutive of it. The sense of place, the felt belonging to a specific geography, a specific community, a specific web of relationships and shared histories and sensory landscapes is not an optional feature of human experience that can be packaged and stored for later retrieval. It is the medium through which human identity forms and sustains itself. The people, the landscapes, the seasons, the languages, the foods, the sounds of a particular place at a particular time of day, these are not decorations around the edges of a life. They are the texture of the life itself. A person who leaves their homeland for another country on the same planet experiences grief. Real grief, documented and studied, with its own clinical name, solastalgia, in the contemporary psychological literature, the distress produced by environmental change or displacement from a meaningful home environment. The grief of emigration has been written about in every language on Earth, in every era of recorded history. The experience of being in a new place, while your old place continues without you, changing in ways you cannot observe or participate in, is among the most consistently painful experiences in the human record. And emigration to another country on the same planet allows for letters, for calls, for photographs, for return visits, for the possibility that the gap can be closed. It keeps both worlds available. It does not require the emigrant to choose permanently. Departure from Earth at interstellar velocities is not emigration. It is not exile. It is not even the most extreme form of earthly displacement. It is a severance of a kind that has no human precedent, no cultural framework to absorb it, no psychological literature derived from people who have survived it and reported back. The crew departs, knowing with mathematical certainty that the world they are leaving will be, at minimum, 40 years older before any two-way communication can complete a full round trip. They depart, knowing that anyone over the age of 40 at departure will almost certainly be dead before the vessel arrives. They depart knowing that the children born in the year of their departure will be middle-aged or elderly by the time the mission completes. They depart knowing that the institutions, the governments, the cultural landscapes, the cities they knew will have transformed beyond recognition. They are not going somewhere and coming back. They are going somewhere, and the somewhere they left is, in every meaningful experiential sense, already gone. And yet people would go. This is perhaps the most striking feature of the entire accounting. Against all of the physics, all of the engineering, all of the biology, all of the psychology, all of the existential weight of permanent departure, people would go. They have always gone toward the unknown, across every horizon that presented itself, in vessels that were almost certainly inadequate, for reasons that were often unclear even to themselves. The original Polynesians who navigated open ocean in outrigger canoes without instruments, reading stars and swells and birds and the colors of the water, setting out into a Pacific that had no known far shore they went. The first humans who crossed the land bridge from Asia into a continent that no human being had ever seen, carrying nothing but what they could make and what they knew they went. The first person who climbed to the top of a mountain range and looked at what lay on the other side and felt, not fear but something that functioned like invitation, that person went. The impulse is ancient. It is not rational in the sense that it consistently optimizes for survival. It is not consistent with the kind of measured risk assessment that a modern engineer applies to a mission proposal. It is something older and more stubborn and less easily dismissed than either of those things. It is the feature of human consciousness that has, repeatedly, defied the perfectly reasonable objections of everyone who understood the danger clearly and gone anyway, and in going, discovered that the world was larger than the boundary of the known. The journey to Proxima Centauri does not become less terrifying in light of this. The terror is real. The obstacles are real. The distance is 24.9 trillion miles, exactly as wide as it was when we began this journey, unchanged by anything said or thought or calculated in the hours since. The energy requirements have not declined. The biological fragility has not resolved. The loneliness of the void has not softened. The faces of everyone left behind have not stopped belonging to a world that will continue without the traveler, changing without permission, aging without pause, completing its unfinished business with or without the people who have gone. The nearest star offers no comfort on these terms. It offers only itself a dim, red dwarf burning in the darkness, patient beyond all imagining, attended by at least 2 worlds, one of which may be habitable, all of it surrounded by 24.9 trillion miles of vacuum that does not care whether anything ever crosses it. But here is what the terror does not cancel. The fact that we know all of this. The fact that the Lorentz factor is a solved equation and the mass of Proxima Centauri is a measured value, and the orbital period of Proxima b is a confirmed 11.2 days, and the atmospheric composition of that world is something we will soon be capable of detecting from here. The fact that Robert Innes, working with photographic plates in Johannesburg in 1915, could measure the parallax of a star so dim it is invisible to the naked eye, and derive its distance to a precision that still holds. The fact that a schoolteacher in Kaluga, in 1903, working alone in the hours after his students went home, could derive the mathematical structure of rocket propulsion from first principles. The fact that a patent clerk in Bern in 1905, rejected for academic positions, could deduce the geometry of space-time from a thought experiment about a moving train and a beam of light. The distance to Proxima Centauri has not changed. What has changed over the century since Innes first measured it is the precision with which we know it, the depth with which we understand what it contains, and the clarity with which we can articulate exactly why it is so difficult to cross. We have not closed the gap. We have mapped it. We have described it in mathematical language of extraordinary precision. We have detected the planets that orbit at its far end and begun to measure their atmospheres with instruments sensitive enough to find the molecular signatures of biology in the light that passes through a planetary atmosphere, 4 light years away. We have done all of this from here, from this small, improbable, extraordinarily fortunate world orbiting a medium star on the outer arm of a spiral galaxy that contains 400 billion other stars. The human species is, in the most literal sense, the part of the universe that has developed the capacity to measure itself. We are the cosmos become conscious of its own dimensions. We are the matter that assembled into something capable of asking how far away it is from other matter, and then actually figuring it out. That capacity, the capacity to measure, to calculate, to understand the exact shape and scale and content of a universe that is under no obligation to be comprehensible, is not a small thing. It is, arguably, the most remarkable thing that has happened in the 4 billion year history of this planet. It does not make the crossing easier. It does not shrink the distance. It does not solve the rocket equation or conjure the energy required for relativistic flight or heal the biological damage of decades in the interstellar void. It does none of those things. But it means that when we look at Proxima Centauri, that dim red point invisible without a telescope, burning its hydrogen with the slow patience of something that will outlast nearly everything else in this part of the galaxy, we are not looking at an unknown. We are looking at a known. We have measured it. We have named it. We have found its worlds. We have begun to read the light that passes through the atmospheres of those worlds and search it for the signs of something like us. The nearest star is 4.24 light-years away. The nearest star is 24.9 trillion miles away. The nearest star would require 73,000 years to reach at Voyage's speed, 6,400 years at the fastest velocity ever achieved by a human spacecraft, 42 years at 10% of light speed with a propulsion technology that does not yet exist, powered by an energy source that would require the full output of the sun to produce in meaningful quantities. The nearest star hosts a planet in its habitable zone, whose surface conditions are unknown, whose atmosphere may have been stripped by billions of years of stellar flare activity, whose capacity to support life remains one of the most consequential unresolved questions in the history of science. And the nearest star is right there, fixed in the southern sky, rising and setting with the rotation of the Earth, present in the same location it occupied when the first human being looked up and, for reasons we will never fully understand, felt the stirring of something that could not be satisfied by staying. Proxima Centauri will be burning when every language currently spoken on Earth has been replaced by languages not yet imagined. It will be burning when the last ruins of every city built by human civilization have eroded to geological traces indistinguishable from their surroundings. It will be burning when the sun has swollen and scorched the inner planets and shed its outer layers and begun its long cooling toward a white dwarf. It will still be there, dim, patient, unchanged in any timescale, relevant to human ambition when 4 trillion years have passed from this moment. The distance it sits at will not change. The physics governing the crossing will not relax. The energy requirements will not diminish. The human body will not spontaneously evolve the radiation resistance, the zero-gravity adaptation, the psychological endurance required to make the journey trivial. None of the hard things will become easy. They are not waiting to become easy. They are simply what the universe is, and the universe did not design itself around the preferences of a species that evolved on a rocky planet over the course of a few million years and looked up one day and decided it wanted to leave. But looking up is not nothing. Measuring is not nothing. Understanding, with genuine precision and genuine depth, exactly how far away the nearest star is and exactly what it would cost to reach it, that is not nothing. That is, in fact, everything we currently have. It is an honest reckoning with the universe as it actually is, rather than as we might wish it to be. It is the beginning of whatever comes next, even if what comes next is centuries or millennia away. Even if what comes next requires transformations in human civilization and human technology and human understanding that none of us alive today will witness. The terror of the journey to the nearest star is real. It is justified. It lives in the physics and the engineering and the biology and the psychology and the existential weight of permanent departure from everything that makes a human life feel like a human life. None of that terror is dishonest. None of it is exaggerated. But somewhere in the darkness, 4.24 light-years away, a small red star is burning. Around it, at least one rocky world completes its orbit every 11 days, passing through the habitable zone, receiving whatever light the dim star provides, sitting in a silence that may or may not be empty. We do not know yet what is there. We are building the instruments to find out. We are doing the mathematics to understand what it would cost to go. We are, slowly, honestly, precisely, mapping the full shape of the problem we face. That is what it looks like when a small, fragile, extraordinary species decides that the darkness is not a reason to stop looking. The nearest star is 24.9 trillion miles away. We know exactly how far that is. We know exactly what it would take to cross it. We know exactly what waits on the other side, in the dim light of a star that will outlast nearly everything else in this galaxy. And we are still looking. That is not a small thing. That is perhaps the only thing that matters.